Yeah, I think they're in this PowerPoint too, but we've already gone through here. And we're almost through with this guy right here. Row, 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 row. So what's the first thing you have to do when you start a new program? I'm waiting. So y'all have already did at least one program down there, right? What's the first thing it asks you to do? Huh? Choose your CPU. So we got two that basically are the same models. We got the 1000, they're both 1000 series. But we got a 1000 and we got 1100. And then we got a B revision on the 1100, right? So first thing you're going to do is choose your CPU. By the way, on this one, let me take the door off. If you got a modular PLC, Alan Bradley loves these numbers. No, I don't think. Here we go. This is this input module right here. Let's say the number. Okay. And this is the actual CPU model. And these would have to use that. And then on the 1100, we can put 4 modules on this thing. So the first thing you would do depends. The first thing you would do when you create a new program is you select your CPU model. And notice here's the numbers right here. So the numbers would be more precise than the actual model number, right? You'll understand that. You come in here and you find the model number. And this is also true on the new version too. And then the next thing I would do, if I had a modular PLC, is I would come up here and I would configure my I/O. So the 1100 requires you to add 4 modules to the side of it. And what you would do when you look these up is you would order them from, and the 1100, by the way, is still being made. The 1000 is not out there, but they have a, I think they call it a nano PLC, which is a fixed PLC, but the 1100 is still available. But these are the numbers that you would be using. So we have a 32-bit. So if I got this number right here, I need to get over here so I'm recording that. If I got this right here, this is a 32-bit 24-volt input module. And it says I can wire it to either do what? Can y'all see this? I can wire it to sync or source. So it's got a common. It lets you set that up depending on what your input devices are. So that would be the second thing I would do. So I'd come in here and I'd select one of these. And then I might even have to configure that. So what I'm going to do here is I'm going to give it a word number. So this is going to be in word 1. Okay. It's not there. What's nice about the, and I'll show y'all, so let me delete this. I hope I can delete it. Okay. So the first thing we do is select the CPU model number. So what we're saying, I might see 1100 PLC, but it might be a bit different model CPU, right? You understand? It's just inside the same plastic pack, has the same. You can buy different models, by the way, depending on how many inputs you have, how many outputs you have. whether it runs off AC or runs off DC, if it's syncing, sourcing inputs or outputs, so on. This is real important to know too. Program contacts that are controlled by a rungs output are simply called normally open and normally closed. The examine if open and the examine if closed are rung contacts that are controlled by a physical input device such as a push button, a switch, push button, or sensor. Everybody understand that? Yes, no? Okay. That's important. Configuring, we're not going to be able to do that. Syncing, sourcing, everybody okay there? Don't understand that? And we talked about the program scan. Look at these two instructions. We looked at the latch and unlatch, right? Latch and unlatch. Every PLC that I've ever programmed had that. They also have a one-shot rising, which we won't talk about this semester, but if you take the PLC 2 class or advanced PLCs, we'll deal with that. And this is the way it scans. So go okay here. So it starts scanning from the, starts scanning rung 0, right? And then it goes across, comes down, goes across, reads the inputs, loads those into an input table. Then it does the logic that's in your PLC diagram, and then it updates the output table depending on what the logic is it's controlling. Everybody understand that? And then it goes to the next rung, goes to the next rung, goes to the next rung, and then when it hits the last rung in the program, it does what? Go back up and stop. And of course, in the Allen Bradley, we I don't know if this is on the 5000 or not. I need to bring that up. But this end instruction right here, this is what's telling it to loop back up. And like I said, that one is automatically inserted. And data files project tree, I had some problems missing this. So this is the project tree over here. And then this is the program, right? You understand that? Now this is where we get in, we really need to understand. This is, and we demonstrated this in the last class. Normally, a stop button is a normally closed push button, right? So we're going to use an examine if closed or examine if open for a stop button. Huh? So an examine if open is true when it's open. And a normally closed push button is not open. It's what? Closed. We're going to use an examine if closed instruction. It's true when it's closed, right? Y'all understand that? This is one of the hardest things for people to understand, especially when they've been through motor controls. Now, when we're dealing with contacts on relays, these terms only apply to input devices, not contact controlled by an internal relay. So a normally closed push button, and I hooked it up here, and I pulled the wire out. I used a normally open push button for a stop button, and I pulled the wire out, and I couldn't do what? I couldn't stop the motor. Y'all remember doing that last time? Well, it gets people in PLCs control because what's the symbol for it? So this guy right here is going to have a problem with that, guys. But this guy right here is using, what's this guy here? This is an examine if open. And he's using a normally closed push button. So this guy right here is going to start off what? False. if you use a normally closed push button. Why is it required to use a normally closed push button as a stop button? So if a wire breaks, it will stop, right? That's a good one. Now this is being controlled by this output port. This is just a normally open contact. This is a normally closed contact. The only time the examine if open and examine if closed instruction comes into play is when you're dealing with input devices. And it's really neat. So how many times can you use can you reuse an input device address? What? As much as you want. And this is what's nice. So a lot of your solid state sensors will only have one contact. But if I wanted to simulate a normally closed contact, then I could use an examine if open, right? You understand that? And they would be swapped around, right? You understand that? So you need to understand that. So yeah, we can repeat the same address all over the place. Output enable, normally closed, normally open, examine if open, examine if closed. But stop buttons need to be a normally closed push button, which means you have to use what instruction and examine if closed. Everybody okay? So just say it's true. So examine if open means it's true if it's what? Open. Examine if closed means it's true if it's closed. Well, a normal closed push button is closed, right? You understand? We want it to be true when it's closed, so we use an examine if closed instruction. It's hard to understand, guys. I understand that. But this guy in this book, he'll draw the circuit, and he'll use a normally closed push button over here, and in his ladder diagram, he'll use an examine if open instruction. So even a lot of people make that. System files, we can't do anything with those. Ladder, we talked a little bit about subroutines, right? Yes, no. And what can we use subroutines for? What's their main use? What's the subroutine's main use for? Huh? Why do we use subroutines for? We don't get to use them to use them. I mean, it gets. What's the main use for subroutines? I can take you over to the FANUC robot over there and show you the programs that run the manufacturing line. And it's got one main program, and all the main program does is just jump subroutine, jump subroutine, jump subroutine. The main use of subroutines is it gives us the ability to take a long program and split it up into individual modules. And that way, and then each module would do a certain task, right? So we moved the FANUC robot when they first installed it, and they came down here and installed it. And we found out right off the bat that the floor over there in H107 is not level. And it's very hard to get a floor that big perfectly level. And what happened is when we moved the robot, which is mounted on the floor, and it's clamped on to the other part of the manufacturing line, when we moved it over to the other side, the robot missed every point. It missed it by an inch. Because that means that side of the floor was an inch lower than this side. So instead of me having to find the point to reteach where it picked up the block, all I had to do was go to the subroutine that's labeled what? Pick up block, and reteach that point. So any big program, so the program's over there. So normally we have a main loop. So this is the actual program that is running one of the lines over there on the Amatro line. And we'll try to make it over there, guys, before the end of the semester. So AGT. Amatro line. Nope, these are diagrams. Hold on a second. Oh, Festo line, sorry. PLC programs. I don't know. I got 3 distributions up here. So here's the first instruction out there, and you'll see what it says. Jump to subroutine. So file 4. I don't have it up there, and this, so all these are all the programs. So over here we got ladder 2, then we got ladder 3, ladder 4, ladder 5, and ladder 6. Here's ladder 3. Here's ladder 4. So this is the subroutine it calls. It's called emergency stop. So if I'm having problems with my emergency stop, then I could go directly to what? And take care of that. This one's called blink. So this is emergency stop blink. And this is file 6. So what it does, it gives us the ability to take a long program and split it up into what? Modules. And then each module should perform a certain task. And it makes the program easier to troubleshoot. It makes it easier to modify. It makes it easier to read. It makes it so much easier to do this. In programming, this is called structured programming. You get into a PLC program, you got 200 or 300 rungs in there, and it's all what? One rung, and you're having problems with one section, and you got to do what? You got to go all the way down those rungs and find the section of the ladder diagram that takes care of that. And if you don't cuss, you'll start cussing, because these guys, you know, if I had a programmer that did that, then they wouldn't be a programmer around me very long. Because I had to go back and troubleshoot these straight line programs that people don't do what? They don't split them up in subroutines. You know. Now the number of ladders you can have on the fixed PLC, these right here are fixed. These are fixed. On your modular, on your other PLCs, you're not the PLCs that's not fixed. Then you can keep adding. You can keep adding ladders until you run out of memory. So it all depends on how much memory you got in your PLC. They didn't split this one up, but so this one's got 36 rungs in it. Now whether this can be split up, I don't know, but now notice they use symbols, and then they use comments, right? And the comments are both in English and German. Of course, I know Festo is a German company, right? Huh? You didn't know that? That's where we went, though. Yeah, okay, these different data files. We have I for input, O for output, S2, S4, C5, R6, F8, and B3. It says B3 and B10, guys, but you can make as many of these as you want to if you have enough memory and you're not dealing with a fixed PLC. The S2, these are system files. You can't do with that. But you can make more timer files, data files. You can make more counters. You can make more control registers. You can make more integers. You can make more floating points. You can make more what we call bit files. I showed you how to do that, right, on the 1100. How did we tell you how to do that? Now the 1000, you can't do this. It's got, I don't know how many data files it's got out there, but I don't know if it's got a long or not. So over here, right over here under data files, you can just right click on that and select what. Now this is using file numbers 0 through 8. So when I come up and add a new file, it's going to ask me what type of file it is. So I can add more timers, I could add more counters, I could add more integers, I can add more real numbers or floating. I got a long file, I got a string file. Strings are text. So if I wanted to send something to an HMI panel or something, a message to pop up there, I would send it text, right? You understand? That's what they primarily use to send information to an HMI panel. ASCII. Primary for PLCs is still ASCII. So, long words. So long words are 32-bit words. These are not available in the 1000, but they are available in the 1100. So it automatically assigns it to 9, but you don't have to use 9. You can come up here and put it, at 200 if you want to. You're controlling it now. And I want a long word. I'll give it a name. And I come up and say OK, and there it is. It automatically adds that down there. So the fixed ones, the ones you can't change in this, is what? 0 through 8. But then after that, if you got the right PLC, you can add more bit files, you can add more binary files, you can add more timers, counters, control registers, integers. You can add those if you need them. So what determines how many of these things you can have? I've mentioned it, but no. How much memory you got in your PLC? So you're going to run out of memory. Every one of these data files eats up a lot of memory. Timers require 3 words per timer, and counters require 3 words per timer. So, and you can put, you're using 8-bit address, and so that's 256 different timers you can have in one data file. And times 3, that would be the amount of memory you would eat up. So, by the way, you can't add more input. The only way you can add more inputs and outputs if you install more modules in there. So you can't add an input data file. Y'all understand that? Because those are physical devices. These devices down here, these are logical devices. And if you don't like it, you can just highlight it and hit the delete key on your on your thing, and you can get rid of the data file. But don't delete these. Well, I guess you could if you didn't do any floating point math, and you didn't need floating point math. Floating point math eats up long words, eats up 2 bytes of memory. 2 words of memory per data file. Per data file. So what that means is you could do what you can delete what you don't need if you need more memory for some of these other things. Now, this is the addressing scheme, guys. We start off with a data file type. Then we put a data file number. Data file numbers are not required for embedded IOs because the PLC knows where those fuckers are at, right? Then we put a colon. Then we put a what? Slot number. What's the slot number for your embedded IOs down there? So embedded IOs mean these are IOs that are inside the PLC. These are not slot numbers. And these are always going to be 0. So your embedded IO will always be 0. Oh, wait, Rich, I thought you said the CPU was in slot number 0. Well, this is not a slotted, or this is not a modular PLC. The CPU does not occupy a slot number. That makes sense. So the slot number only deals with what? These kinds, you know. Followed by a slot number, which is required, followed by a word number. This is only required if your input or your output module has more than one word. So like a while ago, we had a 32-bit input module. How many words would that be? 2. But it's going to be in the same slot, right? You understand that? So you'd say slot 1, right? Then you would have to specify word 0 or word 1. And that's the only thing I've seen where that comes into play. I think the biggest input modules and output modules that Allen Bradley sells is a 32-bit. If you don't need a word, then it's optional. So if you're dealing with bit files, I mean nothing but, if you're not dealing with words, so if all your words are word 0 inside that slot number, then you don't need to provide that. And then if we're dealing with bit files, we put a backslash, right? That's put a forward slash and then put a bit number. Everybody okay on these? Because this is one of y'all had a little problems on that. And this is right. This is not in your textbook. This came out of the manual for the 1100 instruction set manual, which y'all have available to you, by the way, up on Blackboard. Status, this holds the status bits. So if I come up here, of course, this is not running. That'd be a lot going on. Here's the status files. So we can't access those. But this is actually where we can access to processor status. We'll look at a free running clock later on, which is pretty neat. But this is one of our main ones right here where it says errors. You can tell an error on your PLC. Usually a red light will come on from the front and it'll be flashing at you, which means your PLC had some type of error. This is where you would go to right off the bat and see what the error was. And odds are hopefully it's going to give you enough information that you can do what? If it gives you a number, sometimes Allen Bradley pops up a number, and about the only thing you can do is just scan the internet and put the error number in there. Timers, these were put timers. Depending on the size of the PLC RAM, there could be timers with addresses from T40 to T4255. So we're only using 8 bits to address the register. A PLC ladder diagram can access 256 timers. Number of timers may be limited due to the lack of enough RAM in the PLC. Each timer requires 3 words or elements of memory. The book incorrectly calls these words registers. The registers are inside the CPU and not in memory. The PLC manuals calls these elements. So this guy, he does a really good job at, you know, I've written a book before and published, and I understand these little quirks that can be in there. You know, everybody okay there? So we'll play around with timers after we get through with logic. Counters holds information related to counters that can have an address from C50 to C5255. Numbers may be limited by the amount of RAM. And by the way, and this is what I showed you, data files 9 through 255 may be available for counters on some Allen Bradley PLCs. So if you got an 1100, you can have timers from 9, and you can't have anything below 9 because those are already occupied by the preset data files, right? And I've told y'all this also, is that this is one thing that that programmers automatically started having problems with, is that RSLogic 500 dedicates data files, and you've got these data files, and that eats up a lot of memory. Well, if you're not using floating point or real numbers, or you're not using this or not using that, it still eats up that amount of memory, right? You understand? So your newer PLCs, they don't specify memory. They don't give you these data files. They assign memory when you add it. So if you added a counter, it would assign enough memory to handle that counter. And if you only had one counter, it would just use the amount of memory for one counter. Here, automatically, you use 256 times 3. It's built in, so that much memory is in your eat up by your counters, even if you don't have a single counter program in your PLC. So this is one of the biggest changes between RSLogic 500 PLCs and then the new RSLogic 5000 is they don't assign memory. They assign memory when you use it, right? That makes sense? So it manages memory a lot. The newer PLCs applications manages the memory a lot better. Control registers. Control registers holds 256 words. R6 through R used to control used as a control register. The control register holds. This is not. I need to refresh it. There we go. So R6, we won't be using R6 this semester. If you do the, if you take the IoT 212, which is advanced PLCs, this is where we'll get into bit shift instructions, sequencers, shift register instructions, and we'll get into some more advanced instructions. So about all we're going to get through it this semester is up through counters and timers. That's as far as we'll get, which will probably get you through quite a few different programs. If your company wants you to go ahead and get this advanced where we get into the math, these PLCs, so everything that we're doing this semester we could do with relay logic. Counters would be hard to do with relay logic, but timers, we have timers that we do that. But a PLC is a computer. So not only can it simulate all the inputs and outputs, it also can do math. It can do logic that's more in depth than what we're doing in this class just by using contact logic. It can do what we call compare instructions. Say if this is true and this is false, do this. It can do shift instructions where we shift all the bits inside a number to the left or the right. It can do interrupts, which we don't understand, but we'll talk about that in PLC 2. There's a lot that these things can do because they're computers and they're not relays. We don't have time in this class to get through with all that stuff. We will be playing with integers a little bit. And what's an integer? Y'all should have had that in math somewhere. It's a sign. It can be signed. It has no fraction. So integer numbers has no fraction. Sign numbers between, if we're dealing with, so let's do that. So how many combinations can we represent with 16 bits? Let's take a break. So how many combinations could I represent with 16 bits of binary? I'm waiting. So look at your chart. Look up 2 to the 16th. So what's 2 to the 16th? Now, how can we represent a signed number? So you have to remember everything in the computer is nothing but ones and zeros. So there is no such thing as a plus sign and a minus sign. So your calculator is binary, but yes, it's got a plus sign and a minus sign on it. So what we have to do is we have to sacrifice one of the bits to indicate a signed number. Now, which would be the obvious one to sacrifice if I've got a 16-bit number? So this is a 16-bit binary number. Which one would be the most obvious to sacrifice to indicate if the number is positive or negative? The far left one. And this is the way it works, guys. If I'm dealing with a signed number, if this is a 1, it means the number is negative. If it's a 0, it means the number is positive. So that gives me 2 to the 15th to recognize numbers. And what's 2 to the 15th? 32,768. So that means I get 32,767 positive combinations, and I get 32,768 negative combinations. Why do we have one more negative than we have positive? It starts with 0, and 0 is the only number that's not signed, but it eats up one of your positive combinations. So if you divide 65,536 by 2, you come up and get 32,768, but you lose one of your positive combinations for what? For 0, because the most significant bit is 0. So when we deal with signed numbers in computers, we'll always have one more negative number than we have positive numbers. So if I go to a long word, that's 2 to the 32nd, that gives me this many combinations, but I have one less positive because we lose 1 for 0, right? Everybody understand that? So this will come up. We'll have one more positive number than we have, one more negative number, positive numbers, because so when we have integers, the N register is an integer file, but it's a 16-bit file. So the biggest thing you can have in that integer file is a positive what? 32,767 or a negative 32,768. If you go past that, you're going to have what we call an overflow. And we'll learn what happens there. And this is long words, but I've already talked about it. So the 1100 and this PLC right here supports what they call a long word, but it's not one of your data files. It's not one of your default data files. you have to create a long word. And that's what I did a while ago. Okay. Any questions? Floating point. Floating point uses a 32-bit long word, but it creates an exponent of 7 bits. Uses 7 bits for the exponent. It uses 23 bits for the mantissa, I guess you'd say that. And it uses 1 bit for the sign bit. Okay? So that gives us this range right here. So this is binary, this is decimal, this is decimal. So it's going to say 10 to the 38th because that's what it's going to display. But if we looked at a calculator, that's going to be 2 to the 7th. That's the number of combinations we have for our exponent. You'll see why the X on here. Yes, no? Yeah, y to the X. So I can raise, there it is. So 2 raised to the 7th power, which would be 128. Okay. So we can represent binary numbers from 0 to 128. So if I take 2 and I raise it to the 128th power, that's where we get the, what's that? 3.4028 times 10 to the 38th. So we can represent this. Now what's nice about this is the sign is we dedicate a bit to the sign and it's not part of the number. So we can represent signed numbers from 3.4028 times 10 to the 38 and a minus 3.4028 times 10 to the 38. But as soon as we switch into scientific notation, then which would happen at 2 raised to the 24th. So as soon as I get up above 16,777,216, this guy's going to shift it into another. Just like your calculator. So once your calculator exceeds the range that it can display in 10 digits, what does it automatically do? It switches into scientific notation. Now, what's the problem with scientific notation? You can't see the whole thing that's rounded. So scientific notation is not as accurate. Right? You understand that? Yes or no? So that's where all these numbers come from. So these are floating point numbers. But they have a limited range, right? B3 files or bit files, each holds 256. The book teaches B3 and B10, but literally if we've got the right PLC, we can have B3s from up to 255. And then I can actually add another B3 file above 9. B3 files, we use these for our bit instructions. These are internal coil. What is an internal coil? We've talked about this several times in this class. So what is a control relay? What's a control relay? I'm listening. We're going to talk about that. Well, a relay is an electric switch. We have 3 categories of relays. We have a control relay. All relays control something. I have a control relay, I have a contact, and I have a magnetic motor starter. That's 3 categories of relays. So what defines it as a control relay? least you're taking a shot at it. Everybody else is just sitting here. So most circuits, most control circuits have two sections. We have a control section that's usually low voltage, and then we have a power section. So we call the name motor controls, right? You understand? But a motor control might have to control a motor. And so the motor relay would be in the power section. A control relay is a relay whose contacts never leave the control circuit. They're not in the power circuit. So I would come over here, and this would be like I'd come over here, and this would be motor controls. And then over here, I'd put a motor starter. And then over here, I would have the power section, and that would be the sensor. These are sensing overloads. And then I'd have contacts up here that's being controlled by this relay. So if I call this relay 1, these contacts are being controlled by M. Over here, this might be 24 volts. Over here, this might be 6,600 volts. So, but if I have a control relay, I could come up here and do this a little different. We'll just call it CR. Oops, I'm sorry. I'm going to put M down here. And I'm going to erase this right here. And I'm going to call this CR. So CR is in the control circuit. This guy's got contacts over here. This is the what? This is the power circuit. So a control relay is a relay that never leaves the control circuit. In PLCs, it's a relay that doesn't need an output. So this guy right here's got 6 outputs on it. And I'm not going to hook a light up to this relay. I'm not going to hook a motor starter up to this relay, and I'm going to sacrifice one of my outputs when I don't even ever hook anything to it. So these are control relays. So what we do in a PLC is we don't use one of our outputs. We use what we call a control relay. And our control relay is our B3 files. So if I was going to come up here, I think I've already, so I'm going to insert this, and then I'm going to put a stop button here. Then I'm going to put a start button here, and then I'm going to put a relay coil over here. Okay. Then I'm going to put a down drop right here. Then I'm going to do what? I'm going to pull this inside. I'm going to put another relay right here. A contact. This is not an input. This is the contact. I'm going to call this input, okay? Then how does it go? Input, colon. I don't have to specify a file number because it's a physical device, right? 0/0. And I'm going to call this stop. And then I'm going to come over here. I'm going to use this input 0/1. And I'm going to call this start. Then down here, I'm going to call this output rich, colon 0/0. And I'm going to give this a symbol run. Oh, I'm sorry. I'm going to call this B3, colon 0/0. I'm gonna just give it a different symbol name. We'll call this run 1. And then over here, I'm gonna just call this run 1. Are y'all following me so far? Okay. Now I want to turn something on. So I'll come over here and I'll put another one right here. Then over here, I'm going to call this run 1. And automatically, once I've assigned it a symbol, then now I can do what? I can use names, right? You understand that? And I'm going to come up here, I'm going to pull an output, and I'm going to assign this to an output. And this is going to control the motor. Okay. So this relay, this is a symbol. This is what we call an internal relay. This is a relay that does not need the output. It's controlled. And I think I told y'all this. When we get into very, very large control programs, 90% of the control circuit is just making decisions. So that means 10% is actually having to drive something, right? You understand? So those 90%, I would not use outputs. I would use internal relay coils. So in PLCs, this is a coil that does not need to do what? Have an output. So you're not wasting one of your outputs. So if I was to come over here and change that to an output, I've wasted an output that's not doing anything, right? You understand? So this is where your V3s come into play. We use these primarily as internal coils, which means they don't use a watt. They don't use an output. Now this is real simple. I could have done this with one relay, but I wanted you to understand what these V3 files are for, right? One function of them. Oops. So check for errors. So I'm going to click on this little thing right here. I'm going to verify the file. Means there's no errors. But if I'd assigned this to an output, it would have still checked okay. It's just that I would have wasted one of my outputs, right? You understand that? And then I got no errors. It don't mean it's right. It means it has no syntax error. That means everything's in the right order. Y'all understand that? So like I said, if I use the wrong output, it has no idea that I used the wrong output. Here, this is an examine if close. So I'm going to come up here and fake a normally closed push button. And then what do? I want to download it. So right now we're offline. So what can we do when we're offline? And some of y'all already ran into this. You tried to change the program when it was in what? Online. And it wouldn't let you do what? Wouldn't let you edit. So to edit the program or to create a program, you have to put your application offline. Everybody understand that? Then to download it, we got two options, guys, and this is what I wanted to show you. And these PLCs, our PLCs by default are in what we call the remote mode. Oops. And so it all depends on the PLC. But if you look at this guy, it's got a switch on it. It's got a key, I'm sorry. Can you see it? And it's got three positions. It's got remote, REM, remote. What that means is you switch the PLC between program and run with your software package. So y'all seen it happen, right? So you download the program, it says you need to switch it to the program mode, and you hit OK, switches it to the program mode. Then it says, do you want to go online? So online is when you put the application online. To run the program, you have to put the PLC in the run mode. Now, some PLCs has a switch right here, which a lot of them like that because I can come over here and put it in run mode, and then I can take the key, right? And now what's that mean? Somebody can change it. They can't change it to the online mode or run mode. I can't change it. We can still go online with it. It's just that I can't make any what with it. Any changes. So the new Compact Logic went back to a key. The MicroLogic 1000 has the MicroLogic 1000 is in the remote mode. The MicroLogic 1100, you can go down to a menu and you can switch it out of the remote mode But the problem is that the keyboard's right there, which means what? Somebody could do what? They could come back and switch it on the remote. So, so here's notes on my keyboard. So on my PLC, I got the remote mode. What does that mode mean? It never focuses. So what does remote mean? Is it focus? Focus. Crap, no. What's the remote mode? You can switch it with the application. So your application switches it to what? The program mode, so you can download and change the program. Then it gives you another option to switch it back into remote mode, right? Run mode to run the thing. Now my application, I've got several modes on my application. I've got offline mode on my application, and what's that? Offline mode is where you can create programs and you can edit programs. You can't edit online. So I've got this PLC in, my PLC turned off. Dang it. I turned my PLC off. So I just got a new PLC. What's the first thing I need to do on my new PLC? I just turned it on. Thank you. First of all, we have to make sure we have the right drivers, but I'm going to have to run this DHCP tool. And I'm going to have to select my network card. I'm going to have to wait for the MAC address for the PLC to pop up. I might have to turn it off, turn it back on. Let's see. Escape. Oh. This is one of those dumb moments, guys. Got to connect the cable up to it. Crossover cable. So I got a C on this, so it indicates it's a crossover cable. Oh, it already popped up. I'm waiting for it to assign an address. Okay, so we should be ready. I'm going to system comms just to see if my PLC's out there. We're trying to anyway. Okay, so there he is right there. See, it gives you the model number here. Okay. So I could do what? Download. Okay. And now it's going to ask me for what? On this one, this is backwards. Most of your new PLC programs, they ask you for the title of the project when you start it. This guy is going to ask you for the title if you save it or when you download it. Now it tells me downloading do I want to download the program, right? Okay. Then we're going to switch it to, so must be switched to the remote program mode to continue. Yes. So it's in remote run, so it's going to switch it into the what? Program mode. Then it wants to know if I want to switch it back to the run mode. And by the way, it's got lights up here. You can actually see it. Do I want to go online? So my application, I can be offline or online. What's offline? I am connected to it. What's offline? That means we can create the program or we can do what? We can change it. What's online? We can actually see what's true and what's false. We can actually see how the diagram, so as soon as I go online mode, it shows me that this contact right here is closed because it's a normally closed push button, right? Okay. Y'all see that? So now I'm actually seeing what the program's doing. I'm going to come over here and just hit the momentary contact on switch 1. It's sealed in B3, right? This is an internal coil. It did not use an output. Brought in this guy right here. Now I'm generating an output and my light's on over here. So what's the 3 modes we can put the PLC in? That's the application. The PLC. Run. What's that? There's no stop. Run. Remote. That's the application. The 3 modes the PLC can be in. It can be in the program mode. That's where you can upload or download the program. It can be in the remote mode, which means you control those modes with your application. And it can be in the run mode. When it's in the run mode, it is running the program. Does the computer have to be hooked up to the computer for the PLC to run the program? Yes or no? Okay, so you go out to Brosa and they got a computer hooked up to every PLC out there. Now, once you switch that sucker to run, it runs the program. I can disconnect that and no big deal. Right, now to download a program into it or to upload a program from it, I've got to have it hooked up. Right? I can write this program and not even be hooked up to the PLC. I can have this computer at home and write my program, come into the shop and do what? Hook it up and then download the program. So what conditions do we have for our application? We've only got 2 conditions for our application. What are those? Offline and what? Online. What's offline? These sound like really good test questions. What can we do in the offline mode? We can edit or change the program, or we can create the program. What do we do on the online? We can watch what's happening with the program. We're actually monitoring the program to see what's true and what's false. It tells us when a run is true. It tells us a line is false. It tells us when a contact is closed. It tells us when a contact is open, right? So the application's only got 2 modes. What's the 2 modes? Offline and online. The PLC's got 3 modes. What? program, run, and remote. Y'all understand those? A lot of times they'll have a key on it where you can switch them. And the only advantage to that is what? You can take your key with you. Except for an Allie Bradley PLCs, every key is the same. That means all you got is what? Whoever has the key. So, okay, we're okay. So let's see how we're doing in lab. What we're going to do next class is we're going to go over, next class we're going to have a test. So we got one more thing we got to go over. Because this is on the test, so we are a little behind, guys. Yes. Yeah, because it's in the remote mode. Yeah, and it's using this guy right here. So this is Ethernet. We call it Ethernet IP. This is Ethernet. Now, there's no such thing as a wireless PLC, but this is just standard Ethernet cable. So any device you use on an Ethernet network, you can use on these. It's usually they're more robust. They handle a rougher environment. So we can have routers. We can hook this up to a router. And then the router could be wireless. So that means I could literally program a PLC from my office and not even have a what? Not even have a cable. If you use a Wi-Fi router, or if you got access to the internet, which is dangerous, then you can have people can literally do what? They can program it from where? From anywhere that they got Ethernet, and that happens all the time. The guy was telling me, I don't forgot where he was working at, but he said they were standing there and all of a sudden things started changing inside the program. And what it is the guy remoted into it, but he didn't tell anybody he was going to do it. And that's not good, is it? So, but yeah, I mean, I can take control of a computer through the internet if it's set up and it's allowed, right? So yeah, they can do it very easy. But it's got to use this. It can't use DeviceNet, can't use Profibus, can't use any of those other older technologies. And this is why Ethernet IP is becoming very, very popular for PLCs. Because now the programmer don't have to be there. The programmer can be at home. The programmer can be up in Chicago somewhere. And they set up the PLC. So who does y'all PLC programming out there? Do y'all have a group? No. They don't. Do they open it up to the outside? Can they do stuff from home? No. No. So you need to really, really protect that really good because, like, if I was to get in there, what could I do? Yeah. So, and all it usually takes is a username and a password. It's what we call a VPN. Just go right into that thing and just make some changes. Y'all don't write those passwords down. Are y'all gonna be involved in program PLCs, or y'all don't know? I know y'all are on those tests. Yeah. So, guys, y'all take a break. Another 10 minutes. So, yeah, we're gonna have to come back here. We got one more. We got one more thing we got to cover. It's on the test. Next lab. Yeah, we have some labs we're going to have to do, which would be a timer and a counter lab. But after that, guys, we got to get to logic. Logic, I think, is the next lab we'll be working on. 2 minutes. You need to get up and walk around. Now we're coming back in here. Let me look at the test and see what's on there.